start off with the notion of a vector valued function. This is section 13.1 of Stewart's calculus. What is a vector valued function? So say you have a function that takes in as its domain real numbers, a subset of the real numbers. So let D be a subset of R. A vector valued function will always output a vector in as many dimensions as you want. As many dimensions as we want. However, in this course, we'll be dealing with 2 and 3 dimensional vectors only. Mostly with 3 dimensional vectors. 3 dimensional vectors in this course. So, the vector valued function, let's call it R with a with an underline underneath it. This is because R is a vector. So it takes in D, meaning D, which is a subset of the real numbers, and outputs numbers in R3. So D is the domain. Now, the domain may or may not be a subset. The domain may or may not be a subset of the real numbers. The domain may or may not be a subset of the reals. So for example, if you have a function, you can have a function that takes in a subset of R2. R2 meaning what it does is that it takes in so let D prime be a subset of R2, meaning all the ordered pairs of this form. R2 meaning all ordered pairs of this form. All ordered these are called ordered pairs. Right, so this R2 is the Cartesian product of R and R. Right, so it could be that R takes in D prime and spits out R3. That could also be the case. However, we'll not consider that case here. But what's most important for as far as we're concerned, for a vector function, is that the salient point, the important point, the salient point, is that the vector function will always output a vector. Right, so this is what's important. Sorry, wrong color. The vector function will always output a vector. Just keep this in mind. For example, in our case, vectors are going to be in 3 dimensions. Vectors are going to be in 3 dimensions. So let's look at a few examples. Let's look at the component functions first. Let's look at the component functions of a vector function, and let's look at a few examples. So for example, you can have a vector function RT RT that takes in, this is T from the domain, right? That takes in T and spits out FT, GT, HT, right? So these are, so FT, GT, and HT, these are what are known as the component functions. Right? So these are known as the component functions. Why? Because FT gives you the x component, right? GT gives you the y component, and HT gives you the z component. Now, because this is a vector function, of course we must have three output components. An example of a vector function, for example, is the following: RT equals t cubed ln 3 minus t and the square root of t. In this case, ft, the x component function, is t cubed. Gt, the y component function, is ln 3 minus t. And ht, the z component function, is the square root of t. Where t is part of the domain D, which is itself a subset of R. Now, the domain D, of course, for the domain for FD is the domain for FD is minus infinity to positive infinity. Why? Because ft, remember, is t cubed. So a polynomial can take on any values in its domain. The domain for gt remember, this is ln of 3 minus t. Now the argument in the ln function has to be greater than 0. So this has to be greater than 3. Alright, and the domain for I'm sorry, t has to be less than 3. T has to be less than 3. Because in that case, 3 minus t is going to be greater than 0. And of course, the domain for ht, notice that h is a function of the square root, is t greater than or equal to 0. So if we combine these three domains, right? If we combine the domains of the component functions, right? We get the domain of the combined function, which is 0, t, 3. So that's the domain. So this is the domain of RT. By combined function, I mean the combination of the three. I mean the combination of the three component functions. Okay, so so for example, if we So this function, this RT, can also be written as you know, as you're probably familiar with, in terms of the basis vectors I, j, and k. T cubed I ln 3 minus t j plus the square root of t k. Right? Now what we do is we look at the limit of a vector function. Limit of a vector function. Right? So how do you define the limit of a vector function? If you recall, we went over the limit of a scalar function. We looked at the limit of a scalar function. Meaning one that outputs real numbers. We looked at this limit in terms of the epsilon delta definition. Right? We saw how we saw how these limits are defined in terms of epsilon delta. Right? So now we define the limit of a vector function. So the limit, so if R t, again same definition, ft gt ht, if this is RT, then the limit as t goes to a of RT equals the limit as t goes to a of ft times comma the limit as t goes to a of gt comma the limit as t goes to a of ht. Right? So according to definition 1, right? According to this definition. So definition 1 is in the book. So according to this definition, we can write the limits in we can write the limit of a vector function in terms of the limits of the component functions. So what do I mean by that? So this is the limit. On the left hand side we have the limit of the vector function right? On the right hand side we have the limits of the component functions. Right, so you can have a let's look at an example of this. Let's look at RT equals 1 plus t cubed t e to the negative t and sine t over t. We want to find the following limit. Limit as t goes to 0 of RT. We want to find this. Now, this is my ft, this is my gt, t e to the minus t, and my ht is sine t over t. So this is actually equal to the limit as t goes to 0 of ft, comma, the limit as t goes to 0 of gt, comma, the limit as t goes to 0 of ht. Right? So what is the limit as t goes to 0 of ft? That is equal to limit as t goes to 0 of 1 plus t cubed. But remember that 1 plus t cubed is a, I'm sorry, I should write this as t cubed. 1 plus t cubed is a polynomial function. So this is actually a continuous function. So this is equal to 1 plus 0 equals 1. Limit t goes to 0 of te to the negative t equals, of course, 0. Because t is going to 0. Right? And the third component function, as for the third component function, the limit as t goes to 0 of sine t over t. Now, this actually requires, so this is a 0 by 0 problem, right? Sine t goes to 0, t also goes to 0. So this is a 0 by 0 problem, so this requires L'Hopital's rule. So if I use L'Hopital's rule on this, I get d over dt sine t divided by d over dt t, which is limit as t goes to 0 cosine t, which is equal to 1. So I end up with limit t goes to 0 rt equals 1, 0, 1. This is actually example 2 from page 890 from of Stewart's Calculus, 9th edition. Now let's look at the definition of continuity. The notion of continuity is defined in a similar manner to that of analogous functions. So continuity is this: limit as r goes to as t goes to a of rt equals ra. This is what continuity means for vector functions. Of course, rt is continuous if and only if the component functions f, g, and h are continuous. Alright? Otherwise, this isn't necessary. I mean, this is necessary and sufficient for limit of for the limit to get to this value, right? Otherwise, you wouldn't get this value. Okay, so now that we've gotten basic ideas about limits, basic ideas about vector functions out of the way, what we'll do is we'll look at space curves, right? If you have a vector function, right? So suppose you have suppose that f, g, and h, right, are all defined, right? Suppose the component functions right, f, g, and h are all defined on a subset of R, right? So f is defined on I, g is defined on I, and h is defined on I. And we want, so the set, so let the set C of all points, the set C, all points x, y, z, right? So this is such that x equals f of t, y equals g of t, and z equals h of t. This is known as the space. This is known as a space curve, right? Space curve, right? So C is a space curve, right? And you're probably familiar with the fact that these are the parametric equations of C. Parametric equations of C. And T is what is known as a parameter. T is what is known as a parameter. Right? So in this case, actually let's plot a space curve, right? And I mean let's sketch a space curve with the direction of increasing t. Okay, let's draw the x, y, and z axes first. So x, sorry. So that's the z-axis, x-axis, y-axis. This is the origin. So let's draw a curve. So this is a space curve, meaning it's a curve in three-dimensional space, right? So the arrows indicate the path taken by the curve. The arrows indicate the path taken by the curve. Curve in the direction of increasing t. Now, if you have only one input variable, parameter, right, you know that it's going to be a curve because you've looked at parametric equations before in 2 dimensions. Now what we're basically doing is we're extending that to 3 dimensions. Now what is RT in this scenario? RT is a position vector of any point P. So for example, if I wanted the position vector at this point P, right? Let's say here T is equal to some number A. So the position vector of this point is given by, let's use a blue arrow, so all the way to P. So the blue arrow, this tells you, the blue arrow is, the blue arrow is R of A, right? So R of A, this tells you position vector at t equals A, right? So so in order to follow around the particle, you'll have to find the position. You'll have to know the position vector of the particle. So the fact that I'm using t is of course quite instructive because t in physics usually stands for time, right? And RT usually RT gives you the position of the, usually RT gives you the position of a particle at time t. Usually in physics. This is in physics, right? So so let's look at an example. This is example 3 from Stewart's calculus. We have a curve that's defined as RT equals. This is example 3 from Stewart's calculus, page 891. Right, so RT is defined as 1 plus t, 2 plus 5t, negative 1 plus 6t. Of course, this is my component functions are 1 plus t, 2 plus 5t, and negative 1 plus 6t. Right, so x equals, if I want the space curve, x equals 1 plus t, y equals 2 plus 5t, and z equals negative 1 plus 6t. Now, what does this give me? Notice that every one of these functions, xt, right, yt, and zt are linear. So this gives you a lot. So this gives you. So the space, actually, instead of saying this gives you, I should say, the space curve corresponding to RT is a line in 3 dimensions. Right? How do I know this? Because all of the component functions are linear. Now, how do we draw that line? Well, we know for a fact that the line, if I set t, we know for a fact that in order to draw a line, we need only 2 points. If I set t is equal to 0, then x equals 1, y equals 2, z equals negative 1. This line passes through 1, 2, minus 1. We know that for a fact. And we also know, by looking at the coefficients of the of t, we also know that the line is parallel to the vector. The line is parallel to the vector 1, 5, 6. Now we know this because remember the line vector is always going to be constant, right? So if I set t is equal to 0, I get 1, 2, minus 1. If I set t is equal to 1, I get so R1 equals 2, 7, 5, right? So if I subtract R1 minus R0, I get 1, 2, minus 1. So I know that this is going to be parallel to 1, 2, minus the vector 1, 2, minus 1. I'm sorry, R1, I'm sorry, just made a mistake. R1 minus R0 is of course 1. Okay, so 2 minus 1 is 1, 7 minus 2 is 5, 5 minus minus 1 is 6. So this is going to pass through 1, 5, so this is going to be parallel to 1, 5, 6, right? Or to 2, 10, 12, or to 3, 15, 18, and so on and so forth, right? So this gives you a line in 3 dimensions. So let's look at another example. The curve whose parametric equations are given by the curve whose parametric equations are given by okay, so let's look at an example in 2 dimensions, right? So this is example 4. So we'll look at the curve whose parametric equations are given by RT equals t squared minus twice t t plus 1, right? So this is a curve in 2 dimensions. If I want to convert this to Cartesian notation, as in y in terms of x, if I want it in terms of y equals f of x, then what I have to do is I have to see the fact that y equals t plus 1, or t is equal to y minus 1, right? And then x equals t squared minus twice t, which is the same as y minus 1 squared minus 2 y minus 1, y squared minus 2y plus 1 minus 2y plus 2, or y squared minus 4y plus 3. So notice that this is basically a quadratic graph with the x and y axes interchanged, right? So you're used to y being some quadratic function of x squared. This is x being some quadratic function of y squared. So what you basically do is you rotate your axes by 90 degrees. After plotting the typical quadratic graph that you're used to, you rotate your axes by 90 degrees. Okay, so there are many examples given here, right? And it's best that you go through them all. I mean, the more you go through, the better for you. So you have the curve whose vector equation is RT equals okay, I'll tell you what. For this, we will plot it using some we'll plot it using software, right? Either we can use Python or we can use Mathematica, whatever you like. So I'll go over the others. I'll plot them. Okay. So I'll give you the code. Okay. So I think it's best we get to section 13.2. Right. So we get to section 13.2. Derivatives and integrals of vector functions. How do you find the derivative of a vector function? Derivatives of vector function. Vector functions. How do you find these derivatives? How do we define a derivative first, right? So dr prime, so dr over dt. So let's say I have a vector function rt, right? So I want to find r prime t. So this is, of course, the same as dr over dt. So I am differentiating with the variable, with the single, with respect to the input parameter, the input variable. So this is, as you would expect, this is equal to limit as h goes to 0, right, of r t plus h minus r t divided by h. Right, now, if, of course, if the derivative exists, I mean, if this limit exists, right? Now, of course, if it doesn't exist, we would like to call it. We call it. We say the derivative does not exist, right? So let's look at. So what does this derivative give us, right? In terms of what does this derivative give us in terms of space curves? So let's look at a let's go back to space. Let's go back to space curves. Let's plot a space curve. Okay, so you have the wrong color. This is the Z. Sorry. Z, X, Y, 0. And so let's plot this space curve. I'll plot it in black. RT, right? RT is this. Just give me a moment. This is RT. This is R of, let's say, T plus H. So let's say at T, the curve is here, and at T plus H, this is R T, this vector, and this vector is R of T plus H. Now, the difference, of course, is the secant, S-E-C-A-N-T, secant, this difference, right? So this difference, by the rules of vector addition, this difference is R of T plus H minus R of T. That's this difference, right? Now, you know from your studies of the calculus with single variable is that as H goes to 0, this secant is going to become a tangent, right? So if you so R prime of T, right? R prime T is going to be the tangent vector to. So for example, if I were to draw this again, right? If I were to draw this stuff again, so this is Z, X, Y. I mean, the diagrams are a lot clearer on page 898 of your textbook. Right, so this is the Z-axis. Keep making the same mistake again and again. Sorry. Z-axis, X-axis, Y-axis. So R prime T, right, remember, is a tangent vector. Sorry, just a moment. So let's say at this point P, the point P is, let the point P be parameterized by T. Let's call this T is equal to T prime, right? So this is R prime at T prime, right? Or using, if let me use better notation, dr over dt at T is equal to T prime. So it's a tangent vector, right? dr over dt gives you the tangent vector. Tangent vector, right? At that wherever you're evaluating it, wherever you evaluate it, right? Now, how do we find dr over dt? Right? How do we differentiate a vector function? So we will use the definition of our limit, right? So let's go back to the definition of our limit. Limit equal sorry, the definition of the derivative, not the definition of the limit. We'll use the definition of the limit, but first we have to write down the definition of the derivative in terms of the definition of the limit, right? So r prime t is equal to, it says h goes to 0, all right? R prime, sorry, r of t plus h minus r of t divided by h, right? With this, do you remember? So we define the limit in terms of the limits. We define the limit of a vector function in terms of the limit of the component functions, right? So these are the component functions. So we'll do the same here. We'll define the limit in terms of limits on the component functions. This is actually equal to the limit. This h goes to 0. Take out the 1 over h. This can actually be written as f of g plus h minus, sorry, f of t plus h, not f of g plus h. F of t plus h minus f of t, comma, g of t plus h, sorry, g of t plus h minus g of t, and of course h of t plus h minus h of t. This h is a number, small number, and this h is a function. So this can actually be written as, in fact, what I should do is I should write them down in terms of x, y, and z. Instead of f, g, and h, let me write them down in terms of the component functions x, y, and z. X of t plus h minus x of t, y of t plus h minus y of t, z of t plus h minus z of t. So this is equal to limit as h goes to 0. So by the definition of a limit of a vector function, I can do this. X of, limit as h goes to 0, x of t plus h minus x of t divided by h, comma, limit as h goes to 0, y of t plus h minus y of t divided by h, comma, limit as h goes to 0, z of t plus h minus z of t over h. But notice that each of these is actually equal. The first of these is x prime t, the second of these is y prime t, and the third of these is z prime t. This is what from, how do you know this? This is from ordinary calculus. It's from ordinary calculus that you know this. Okay, so let's look at an example, right, of how to find the derivative of a vector function. Oh, there's another thing, another concept called a unit tangent vector. Right? It's called a unit tangent vector. So as you know, if you divide a vector by its magnitude, you get the unit vector in that same direction. The unit tangent vector, let's call it at t, let's call it, sorry, wrong color. Right, so let's call it t at t, right? So this is actually equal to the tangent vector r prime of t divided by the magnitude of r prime of t. Right? This gives you the tangent vector, a unit tangent vector at t equals to t. Right? So unit tangent vector here at t, small t, right? So this is going to be extremely useful when we look at curvature and the radius of curvature and so on and so forth. Okay, so all right, so let's go on. Let's look at an example. Right, let's look at an example. So we have RT, example 1 on page 899. So we're given RT equals 1 plus t cubed I plus 1 plus t cubed I comma t e to the minus tj, and of course sine 2tk. Sine 2tk. What is r prime t? Is of course derivative of this guy with respect to t, derivative of this guy with respect to t, derivative of this guy with respect to t. So the first is 3t square. Second, of course, if you use the product rule, so you should get negative t e to the negative t, right, plus e to the negative t. The third, you should get 2 cosine 2t, right? And of course, if you want to find, and the unit tangent vector, so r prime 0 is when at t is equal to 0. So r prime 0 is 0, 1, 2. And the magnitude of r prime 0 equals the square root of 5. So the unit tangent vector at t is equal to 0 equals 0, 1, 2 divided by the square root of 5. Right? So that's the unit tangent vector. So what I expect you to do, I expect you to look through examples 2 and 3 on pages 899 and page 900. Now we're familiar with dot and cross products, right, of differentiation. So on page 900, theorem 3, right, theorem 3, page 900, you have a bunch of formulae. Right, so let's go to page 900, theorem 3, page 900, right? So you've got this bunch of formulae. 6 formulae regarding differentiation of vector functions. We can, so let's look at how to how we can approach the so I hope you're familiar with the dot and cross products, right? So so let's look at the proof a formula 5, right? D over dt u cross dot v cross v equals u prime t cross v plus ut cross v prime t. I think, yeah, that's. I don't think that's been proven here. Alright, so let's look at formula 5. So what it states is that d over dt, right, ut cross v prime cross vt, this is equal to u prime t cross vt plus ut cross v prime t. Ut cross v prime t. How are we going to prove this? Well, notice that so what we can do is we can break it down into its we can break each of u and v down into its component functions, right? So that now we can assume that since it's a cross product, we can assume that u and v are three-dimensional vectors. So let u be equal to, so let ut, we'll call the component functions u1, u2, u3, right? u1 t, u2 t, u3 t, and of course vt, we'll call it v1 t, v2 t, v3 t. So these are component functions, right? So u cross v, ut cross vt is of course equal to, so if you take the determinant, so we'll assume that the u1, u2, u3, v1, v2, v3, they're functions of t. I'm not going to write t every time. So this is equal to u2 v3 minus u3 v2, comma, and then you have negative u1 v3, right, plus v1 u3, comma, and then you have u1 v2 minus v1 u2, u1 v2 minus v1 u2, right? So in order to differentiate this, we'll have to differentiate this term by term. So the first term is going to be okay, so if I differentiate this, this is going to be u2, leave this alone, v3 prime plus u2 prime v3 minus u3 v2 prime minus u3 prime v2, and similarly for the second and the third terms. I'll do the first term and I'll leave the second term and third terms as an exercise for you. So is this the this term here, right? So is this consistent? Is this term, is the first term consistent with this formula? Okay, let's call this formula 1. Right, so what is the first term on the right hand side, right? What I wanted to see is what is the first term, I mean what is the first component, the x component of this? What is the x component of this? Is that x component the same as this x component here? Well, let's find out. So u prime cross v, so you have u prime cross v, right, plus u cross v prime, plus u cross v prime. So let's look at the x component. So this is actually u prime cross v plus u cross v prime. This is actually equal to the determinant, the following determinant, right? I, j, k. Alright, so u1 prime, u2 prime, u3 prime, v1, v2, v3 plus I, j, k, u1, u2, u3, v1 prime, v2 prime, v3 prime. Alright, so this is actually equal to, take the I common, right? So u2 prime v3 minus u3 prime v2 plus I u2 v3 prime minus u3 v2 prime plus the j component plus the k component. So the so it's pretty easy to see here that the I component here, right? That the I component here is the same as the I component here, right? So and of course, and I'll leave the j and k components to you as an exercise on your assignment, right? So the complete proof is a complete proof is left as an assignment question. Okay, so the next thing we're going to do now, we're going to actually we're going to prove another theorem first, right? Regarding derivatives, right? So if r of t is if the magnitude of a vector function c, which is a constant, then you have r prime t dot rt dot r prime t is equal to 0, meaning this means that rt and r prime t are orthogonal to each other. So how do we prove this? So remember, the magnitude of RT, right? What is the magnitude of RT? RT, right? This is equal to the square root of RT dot RT. Okay, this is actually theorem 4, right? This is theorem 4. Yeah, theorem 4 on page 901, right? Page 901, theorem 4. So this is equal to C, right? So this tells me that RT dot RT is going to be C square. Now, if you look, I want to let's see what happens if we differentiate this, right? So d over dt RT dot RT equals d over dt c square, but this is actually equal to, since this is a constant, this is actually equal to 0. But what is this equal to? D over dt RT dot RT. Now, equation 4 tells me that the d over dt ut dot vt, right? D over dt ut dot vt equals u prime t dot vt plus ut dot v prime t. In fact, that is proved here. There's a proof given here using the product rule. Since that is the case, using that, using equation 4 from using part 4 of theorem 3, we can write this as r prime t dot rt. We can write the left hand side as this rt dot r prime t. On the right hand side we have 0, or 2r prime t dot rt equals 0, or r prime t dot rt equals 0. Right? So this is what we get from this is how you prove that r prime t and rt are orthogonal. So if the magnitude of the if the magnitude of the of rt is if a vector is constant, then it is orthogonal to its derivative. Right? So one actually, how many? So this is so for example, if in kinematics, right? In kinematics, we have if vt, velocity, is a constant, if the magnitude of the velocity is constant, meaning the speed is a constant, then velocity is is perpendicular to acceleration. Velocity is perpendicular to acceleration. So where do we see this? We see this in circular motion. Right? So in what happens in circular motion? You have something going around in a circle with a constant with a constant velocity, right? So the velocity, let's say, is tangent to the. So this is v. Sorry, with the velocity is varying, but the speed is constant, right? So the velocity of the object is varying, right? But the speed is constant. So magnitude of vt is constant. Now, so this motion is called centripetal motion in physics. Centripetal motion. Now, since it was from high school physics, you know that the acceleration is going to be towards the center of the circle. Acceleration is going to be towards the center of the circle, because and the velocity and acceleration are, because tangent and normal radius are perpendicular, so velocity and acceleration are going to be perpendicular to each other, as in they're going to be orthogonal to each other. Because remember, d over dt vt equals at. Right, so we have covered up all the way to derivatives. From the next class, what I'll do is I'll look at. Okay, fine. We can look at integrals today as well. So how do you integrate a vector function, right? So let's say you have a vector function that's that has three component functions. If you recall, the integral is given in terms of Riemann sums, right? Integral of a function is given in terms of Riemann sums. So what do I mean by that? You take a you take a you take infinitely many intervals, right? And you make those intervals as small as you can, right? Sorry, you take n intervals and you make those intervals as many as you can and as small as you can. Right, so you have a function f, and this you take it at the point ti star times delta t. So delta t, so let's say the starting t0 is equal to t1 is equal to a, and tn is equal to v. Right, so delta t equals v minus a over n. Right, so this is what is known as a Riemann sum. Right, and ti star is a representative point. Right, so ti star is somewhere in between ti minus 1 and ti plus 1. So this is a representative point. So if you recall from single variable calculus that this is going to give me the integral from a to v dt of f of t. Right? Now in terms of vector functions, okay, just one more point is that as n goes to infinity, delta t goes to 0. Delta t goes to 0 as n goes to infinity. Right? So this is how you deal with the Riemann sum. So in terms of vector functions, the integral of a vector function is defined similarly. Right? So the integral of a vector function is defined as such: a b dt rt. Right? I should write rt dt. Rt dt, this is equal to the limit as n goes to infinity, right, and I equals 1 to n, sorry, not infinity, to n, times r of ti star delta t. Of course, where delta t is the same, delta t is v minus a over n, and ti star is a representative point between ti minus 1 and ti plus 1, and sorry, and ti, not ti plus 1, so this should be ti minus 1 and ti. So representative point. Now, of course, this, since this is the Riemann sum definition of the vector function integral, we can actually write this in terms of the integrals of component functions, right? So this summation can actually be written down as limit. So the component functions are f, g, and h. As n goes to infinity, so you have f of ti star. Okay, so you have the summation. I goes from 1 to n, f of ti star delta t, right, plus times I, and then I goes from 1 to n, g of ti star delta t times j hat plus h of ti star delta t times k hat. But this is the same, but this is exactly the same as f of t dt I hat plus g of t j hat plus h of t dt k hat, or is basically these functions in terms of vector notation. In terms of this notation, this later notation, av g of t dt, comma h of t dt. So that's how you integrate a vector function. You integrate the individual component functions. Right? You integrate a vector function. Integrate a vector function by integrating the component functions, the individual component functions, right? So for example, so let's go back to our text, right? And of course, if the small rt is the derivative of capital RT, then by the fundamental theorem of calculus, right? So if you have RT, right, equals the derivative of this guy, then RT by the fundamental theorem of calculus, right? By the fundamental theorem of calculus, I mean, this is a theorem that relates differentiation to integration. You're going to have a to b r prime, sorry, RT dt equals r v minus r at a. Right, so okay, and then of course there's an example. Okay, remember, okay, so if RT equals 2 cos ti plus sin tj plus 2tk, 2 cos ti RT equals 2 cos ti sin tj and 2tk, and if you want to integrate this, right, so this RT dt 2 cos t dt, then you have sin t dt and 2t dt. So now we're doing an indefinite integral, which is also known as an antiderivative, right? So we're finding we want to find the antiderivative of RT. Antiderivative of RT. Right, so the antiderivative of RT equals, of course, this is the first integration is going to give me 2 sine t plus c1, and the second integration is going to give me negative cosine t plus c2, and the third integration is going to give me t squared plus c3, so which is equal to 2 sine t negative cosine t t squared plus some constant vector c. C is a constant vector, and c is equal to c1, c2, c3. Alright, so that's it. What we've done so far is that we've covered sections 13.1 and 13.2 from Stewart's Calculus, 9th edition. Of course, if you have any questions, you can ask during the consultation. And our next lesson is going to be section 13.3, where we will be learning about how to find lengths of curves and curvature and torsion and things of that sort. So, and we will put these ideas to good use. Okay, so thank you very much for listening.